Good afternoon, everyone. Welcome to IME 765 class. Today is May the 4th. First of all, let me stop the video and share my screen. Screen share. Okay. So let's continue. Let's continue our case for. Let's continue our case for the linear regression part of Lasso and the Ridge. And where's my annotate? There's something I cannot find my annotate here. Where's my annotate? Give me 1 second. I need to find my annotate thing, and I cannot find it. Oh, it's here. Okay. So in the last class, we've mentioned the ridge and the lasso, right? And also we've mentioned what? We've also mentioned hello, Zaid. We've also mentioned, the geometric interpretations about the ridge and the lasso. Okay. We also had a look at the, comparison of ridge and lasso in terms of what? In terms of orthogonal inputs. Yeah, orthogonal inputs columns actually, right? And you can clearly see that for that part, actually, which one, lasso is the best, because very clear lasso can do shrinkage as well as what? As well as the variable selection. And also lasso gives a what? Gives a soft threshold. By contrast, ridge is purely a shrinkage, and the best subset selection is what? Best subset selection is actually a hard shrink thresholding, which is I just cut, the first K. That's it. All others, as long as your absolute value is not the largest K, I cut you. That's a hard thresholding. And the lasso is what? Lasso is soft thresholding because it compares it with the, let me see, where's lasso? It compares it with the lambda. Let me see. This is best subset selection, and the lasso should be here. Let me see. Okay, lasso's here. So that here for lasso, why it's a soft thresholding, because you're gonna compare the ordinary solution, ordinary least square solution with a lambda. If you're bigger than lambda, then you keep it. Otherwise, we cut it. So it is not that hard. It's still kind of like user defined. Okay, and after it, we actually introduced the very basic concept of elastic net regularization. Okay, so for the elastic regularization, I think I had a typo here in the last time. Last time I said we must have lambda 1, lambda 2 is between 0 and 1, which is wrong. Lambda 1, lambda 2 times lambda. Actually, if I write in this way, then the lambda 1, lambda 2 here actually equal to alpha lambda or 1 minus alpha lambda here, you know what I mean? So that they don't have to be equal to 1 or something. What you need to make is that both of them is greater than 0, of course. And an interesting thing is that this one, after augmentation, can be written as Lasso regression. I think Arab, is this a homework problem, right? I remember I put it in the homework problem. I have several more problems. I put relatively more difficult problems to the homework, some other problems in the final exam. So, to make your life easier. If you feel this is uncomfortable, you want to, exchange, feel free. I mean, I can put some difficult problems in your final exam. Anyway, so actually by augmentation, this is gonna be the same as, not the same. This is gonna be, can be returned as a lasso form. And augmentation is really a good point. Like ADMM also kind of like augmentation. Anyway, so okay, so today, first of all, let's finish this lecture, which is the last part of this lecture is from the point of view of Bayes estimates. So first of all, this is something that we've already discussed in lecture 3. Suppose my 1i is in this way. Let me make it to single. Okay, suppose my 1i is in this way. No. Suppose my 1i is this formulation, and I assume that the noise epsilon is 0, 1, 0 epsilon square, sorry, 0 sigma square normal distributed IID with known sigma square. And hence, I will have y as in this case, right? Because beta 0 and the beta, suppose they're given, okay? So you clearly have this. The reason I write in this way, beta 0, 1, n, is because I want to, kind of like differentiate beta 0 and the beta, make it more clear. And this sigma square in indicates what? Indicates their IID, okay? And then I will have what? Then I will have this one will be the y given beta 0, beta x will be what? Will be proportional to what? To this part. Why? Because it's what? Nothing but a multinormal distribution, multivariate normal distribution, right? Which is y minus mu. Mu is the mean, this part, times sigma inverse. Sigma inverse is what? Is 1 over sigma square times in, okay? I is the identity matrix with dimensions n. And then times itself, y minus mu, see it? And hence you have this part. And now suppose that we have a prior distribution is in this way. And be very careful. Here, I admit something is kind of like a bit not that clear, is that beta 0 is not, we assume that the beta 0 is not affected and also does not affect the prior distribution, which is here. Because if you make beta 0 to be an element there, then you're going to have exactly the same problem as before that we defined the Lasso. Remember, because your penalty is what? As beta j from j equals to 1 to p. While in your main part of the OLS least square formulation, your beta is from 0 to p rather than 1 to p. Then you're going to have the same problem. And hence, here we assume that the beta 0 is a variable, but is not affected by or does not affect the prior 31. It is 31 here. In the old version, I think I wrote, I added a typo. In the old version, I wrote, where it is? Okay, it's here. In the old version, I think I made it to be, in the old version, I made it to be 31, 30 here, I think it is here. And I corrected it to be 31. When I added the label, added it to a wrong equation, beginning equation structure. So that in this case, I will have this. And by Bayes' law, very easy. I have this part as proportional to what? Proportional to the likelihood times the prior, right? And if you just make them together and do some math, for example, you take this one over negative 1 over 2 sigma square out, and then you're going to have this part. And guys, have a look at this. What is this? What is this? This is exactly nothing but what? Ridge regression. Why? Because how would you determine this beta 0 finally? This is proportional to this in terms of MLE. What do I want to do? I want to maximize this likelihood, this density function, right? Maximize this density function. Before it is the constant, not related with beta 0. Ignore it. Of course, that's positive. And the second part is what? The second part. Sorry for the noise. The school there, I don't know what they are doing. They're decorating something, so it's very noisy here. The second part here, exp part, I want to maximize this part. That means what? I want to argmin this part, the underlying part here. See it? Why? Because I have a coefficient negative 1 over 2 sigma square. So the argmax becomes argmin here. Okay, from argmax to argmin. Hence, I want to argmin this part. And then this is exactly the same as the ridge regression. See? Where lambda equals to sigma square over gamma square. See it? The key here is that I assume that the prior distribution of beta is 0 norm with gamma square, with tau square, sorry, this is tau, with tau square RID distribution. That is the key here. So that in this case, we can say that we can see that from this setting, which is first the noise. First, this one, y expression is this, and the noise is 0 sigma square ID, and the prior distribution is also 0 tau square, also ID. Then in this case, the what? The Bayes, in terms of Bayes estimate, using the MLE, okay, we have what? We have exactly the ridge regression, where lambda equals to sigma square over tau square. See it? And hence, in terms of this is nothing but what? But ridge regression. Okay, then you may say, hey, this is somewhat like unfair. Why? Because remember, in Bayes estimates or Bayes inference, what we usually do? What we usually do is that after getting the posterior distribution, what do? We use the mean, right? We use the mean to estimate to have a point estimate for the beta. Instead of, let's say here, I use the MLE. You may say it's unfair. Remember what I'm talking about? Let me show you here. So this is lecture 3. And here, let me see MLE and the Bayes. Okay, Bayesian methods for parameter estimation. And we usually do, what we do is here. Let me see where it is. I wrote it here. Where did I write it? Let me see. I just remember the conclusion. Oh, okay, here you go. In many cases, however, we prefer to get a point estimator. So in this case, a natural way is to use the mean of the posterior distribution to be the point estimator. This is the Bayes estimator. See it? So in many cases, in most cases, actually, when we're talking about the Bayes estimator, we're talking about what? We're talking about the point estimator using the mean instead of MLE, right? So what's going to happen if we use the mean instead of the MLE here? Otherwise, you say it's unfair. Okay, good. So first of all, this example is a special case of example 3.4 in lecture 3, the same lecture. Let me show you. It's right here, I think. Yes, right here. See, exactly the same. Why it's a special case? Because here we assume that sigma epsilon here doesn't have to be independent. It has a square. It has a covariance matrix sigma square. Sigma. See it? But have a look here. I assume that all my epsilons are what? Are IID. They are independent. So this is a special case of this, right? Okay. Then you can see the y set here. Let me see where the prior distribution, the beta set here is the same. That I assume beta is this and this. And also it's a special case. Why? Because in our example here, mu1 equal to 0, and the sigma 1 square, sigma 1 again is what? As independent. We set it to be tau square I. Tau square IP, if I remember it correctly. Let's see. Yeah, it is follows what? Follows normal distribution with 0 mean and the tau square IP. See it? While here it is mu1 and the sigma 1 square. So it is a very special case. Okay, now let's have a look at the conclusion of the general case to see what happens here. In the general case, I have what? I have this, right? So this is what? This is a normal distribution. See it? Very clear normal distribution with what? With mean equal to nabla eta, and the sigma. I mean the variance as eta. See it? Sorry, this is lambda, not eta. Sorry. This is lambda. I think I have a more clear conclusion here. Let me. Give me 1 second. Let me make it to be this mode. This mode. Okay, so it is here. From here, you can see actually this. The posterior distribution still follows multivariate normal distribution, which is mu as lambda eta, and the covariance matrix is eta. So it's still variant. So it's still normal. And in this case, what is your mean? Your mean is eta as lambda eta, right? What is lambda eta? Lambda eta is this part. See it? And come here. Have a look at here. This part is what? This part is this. Something inside. You know what I mean? What I mean is this. So I want to minimize this part. Okay. Now what is this part? What is the solution of what is the minimizer of this part? Isn't it beta equal to eta? Beta equal to lambda eta, right? Why? Because clearly this one is PD, is positive definite. The eta lambda inverse, it's positive definite. So that this one's convex. Because this one's convex, so it has a unique global minimize. It has a global, not necessarily unique, unless it's a strict. Yeah, actually, let me think about it. It's. Let me think about it. It is. Yes, it must be global. The minimizer must be a global minimizer, and then my beta equal to nabla tau. No, sorry, eta. Sorry, I get very confused about the notations here. To write it is easier than to read it. About the lambda eta, right? So lambda eta means what? Lambda eta is nothing but the solution of this problem. See it? And this lambda eta, from this general conclusion, you see what? This lambda eta happens to be the mean of this normal distribution, of the posterior distribution. See it? And hence you get a what? And hence you can conclude that this beta hat and the beta 0 hat must be what? Must also be the solution of the mean, must also be the mean of this normal distribution. In other words, the solution of the rigid regression here is both the solution of the MLE, maximum likelihood estimation, and also the solution of Bayes estimation. They are the same. Get a point here? And hence, we conclude that it doesn't matter you use MLE or you use the mean to estimate the point, to have the point estimation for beta 0. In terms of this setting, both of them are equivalent to the ridge regression. And hence what? Hence we conclude that in terms of Bayes estimation, ridge is the best. Then you may say, hey, you claim ridge is the best. It's unfair because you have not shown me, let's say, how about Lasso or some other cases? Okay, great. Let's consider an even more general case. Let's consider this 27, which is here. So the first part here is very clear, the least square part, and the second part, I make a Q here. So very clear, if Q equals to 2, it is ridge, Q equals to 1, it is Lasso. Very clear, right? Let's see what's gonna happen. If I set in this way, guys, be careful. I cannot simply set it the posterior in this way, because if I set the posterior in this way, then I will turn out to get a ridge again. I don't want to have a ridge anymore, right? Because I want to compare with the general case. So in this case, in order to make this part to be Q norm, to the power of Q instead of 2 norm, what I'm gonna do is that, what is that? Okay, what I'm gonna do is that I'm gonna use a smart way that I'm gonna set the prior distribution of the beta to be what? To be exponential of beta j, let's say, to be the exponential of beta j, absolute value of beta j to the power of Q, because I need a Q here. What I mean is here, have a look at here. I'm gonna set the prior distribution of beta j to be this. The noise epsilon is still the same, follows normal distribution with mean 0 and variance sigma square, okay? But my prior distribution is gonna be in this way, for j equals to 1 to p. Again, exclude beta 0. So what we're gonna have is that if you make it in this way, then how about the whole beta? The whole beta, again, beta is from 1 to p, not 0, okay? You're gonna have what? You're gonna have the summation of the j of this one, right? See it? You're gonna have this part. And then here, you're gonna have a negative 1 over 2 sigma square times this part. You know what I mean? Why? Because of here. Because you get from this part, see it? You're gonna have this part. You're gonna have this part. And then after it is gonna be, let me write it. Please tolerate my very ugly writing probably. To be ugly writing. Plus, let me write it a bit slower. Sigma j equal to 1 to p beta, oh my god, j to the power of q. Okay, you know what I mean? So you're gonna have this part, and then what you're gonna do is that you're gonna take the 2 sigma square out, and then you're gonna take the sigma square out, so that you're gonna have a sigma square here. Why? Because you take this sigma square out, okay? And hence, what do you have? You're gonna have this part. You're gonna have this part, okay? And that's the reason why in this case, it doesn't matter what is your p here, you're gonna have this. And clear, from this point of view, we see what? What is the difference between Lasso and the ridge, or whatever you want to call? Actually, it's just from different prior distribution. See it? So that's in terms of Bayes estimates, we see the main difference is a different prior density. If Q equals to 1, which means the Lasso, this prior is actually called a Laplace distribution. You can see it. Laplace distribution has some very, very interesting, cases. And the second thing is that in the ridge part, we mentioned that it doesn't matter. You want to, estimate the ridge. It doesn't matter if you want to estimate the beta hat to by, let's say, MLE or by the mean, which is our traditional Bayes estimation method, right? They are going to be the same. Both of them would be the ridge regression. However, here, if you want to use the mean to be the point estimator, then you will not get the Lasso back. In other words, ridge, in terms of this form, in terms of 27, this form, ridge is the only case that for the ridge, for the Bayes estimates, the traditional Bayes estimates, in which we use the mean of the posterior distribution to be the estimator, ridge is the only thing that are gonna get the same result. And hence, I can conclude that in terms of Bayes estimation, ridge is the best. Get the point here? So this is to give you something different. Before, we always say that Lasso is the best, everything Lasso is good, good, good. But in terms of Bayes estimates, ridge is the best. All the proofs are here. Okay. Regarding the detailed math, please, I need to save some time. Please, derive this by yourself. Again, you must derive it. Don't just look at it or verify it. Instead, challenge it. Okay. Take a piece of paper and derive step by step by yourself. Okay. So so far any questions here? This derivation is almost exactly the same as here. If you know how to derive this one, for sure you know how to derive this one. This is much, much simpler than this one. Because here, you need a trick here. Remember, at the time I showed on the whiteboard here, you need a trick here. This is not that easy. You need some time to, add and minus plus something to play it with. But this is too simple. The part here is too simple. The part 2 here, everybody can see it. You just direct multiplication. Everybody knows how to calculate. Okay, so this is really much, much simpler than this case. Any questions here? And once you have this one, you can really see that they are both, for the ridge part, they are both MLE and also the mean. And hence, no matter use MLE rule or use the traditional Bayes rule, which takes the mean of the posterior to be the point estimator, for ridge, they're exactly the same. But for Lasso, they are very different. For in which the prior distribution is a Laplace distribution. Okay. Any questions? No question? Okay. So here's everything about the supervised classification. So sorry, about the supervised learning part in this class. Again, due to time limit, I don't have enough time to introduce more things. Otherwise, I would definitely put a little about the trees. And also, I will definitely put something about model selection inside. But unfortunately, I don't have so much time. And after it, we're going to introduce the unsupervised learning, okay? Okay, let's go to the part of unsupervised learning. A brief summary of the supervised learning is that for the supervised learning, we basically introduced 2 parts. First part is what? Classification. The second part is regression. And actually, you can see many classification methods, especially for the logistic regression, LDA, these kind of things, we actually operate them in the form of regression, right? Okay, so for supervised learning, we have a teacher. We learn from a teacher. This teacher is what? This teacher is actually Y, the Y response vector, or sometimes you can call it a matrix, in case that you have multiple responses, something like this. Remember what we mentioned in linear regression too, that we have multiple level of the responses, right? So this Y gives us what? Either directly give us the answer. For example, in classification, it directly tells you, okay, this data, the classification, the label is 1 or -1, positive 1 or 0, whatever. Or sometimes if it doesn't give you directly the correct answer, at least it gives you what? It gives you an error measure. That means, okay, so the y value of this data, for example, equal to, for example, 1.2. And use your regression model, you estimate it to be, for example, the value is 1. So what is the error? The error is 0.2. And then, for example, you can use, let's say, the expected loss, the loss function. The most common loss function is what? Is L2 loss, right? Which is here. So you can use this kind of methods to what? To measure the error. This is how you learn from a teacher, okay? Which is, supervised learning. In addition, another point of view about the supervised learning is that some cases we want to estimate this, P of y given x. In this case, we consider what? We consider x and y follow some joint distributions. Of course, you don't know this joint distribution, and you are more interested in the probability, the joint density actually, which is given the x, what is the y? Why? Because in your future prediction, you will really have another x, and then you're gonna be asked, what is the label of it? Or what is the, let's say, corresponding response of it in terms of regression, right? So you're more interested in P of y given x, this distribution. Usually we do it as what? By Bayes rule, and then we're gonna make it to be Px and y divided by a, let's say, support, right? And we can ignore this support. Why? Because this support is nothing related with, my parameters here. And we can do the things. We almost never, actually in this class, we never consider this, directly consider Px. Why? Because again, we're talking about a model, which is y equal to fx given theta. Px itself is not related with theta. The y is related with theta. So that this Px part is usually in the support, and then we just ignore it. Remember, we just wrote what, for example, here, as we just wrote, as a proportional to something. Why we write proportional? Because we already ignored the what? The denominator, which is exactly this part, the Px part, because that's not related with the beta, not related with our variable. So I ignore it. Okay, so these are the things from supervised learning that y does give you information, which plays a role as a teacher. Now let's have a look. What does unsupervised learning mean? In unsupervised learning, we are learning from the data without a teacher, in which we only have what? We only have input matrix or input data x. That's it. You no longer have a y. The good point is that you no longer have p plus 1 here. So you only have the p, which is a better thing to save your life. But the bad point, very bad point is what? The very bad point is that you only have this x. And you may say, okay, so without a y, without teacher, so what? I'm very smart. I can also learn, right? There's a big problem. How would you measure the success of your learning without the teacher? Okay, with the teacher, I can say, for example, okay, read chapter 1. When chapter 1 is done, I'm gonna give you some exercise. You can finish all my exercise. You can say, oh, congratulations, you have learned this part successfully. The question is what? The question is now you don't have the y response. How would you measure the goal? How would you measure the goodness or the success of your learning? So as the example that I just mentioned is the case of, for example, you read a book by yourself. How would you really think that, for example, you learned very well? Suppose there's no, instruction. Suppose there's no, for example, exercise. So if we go back to the data, that means we don't have something, for example, as a loss function here. Remember, here usually how we do it, we make, for example, p, x, y, and then we feed it by what? By minimizing the expected loss, right? But here you cannot define a loss function, or you cannot define an objective loss function. Why? Because you don't have this y response. You know what I mean? You don't know how to evaluate, and hence in this case, actually, in many unsupervised learning, these kind of measures are subjective. Okay, subjective rather than objective. It's subjective, unfortunately. And if in this case, if we can define something like what I'm going to mention later about similarity or dissimilarity, then we can use this part to define the goodness or success. For example, then we can use the, for example, L2 loss function to measure it. But how would you define this goodness? How would you really define this, similarity or dissimilarity? Different people may have different way. That is a problem caused by without a teacher. You know what I mean? Without a common measure. That's a key problem, or also the key difficulty of unsupervised learning. And that's the reason why in unsupervised learning, based on the same objective, based on the same thing, different people may have completely different systems to measure it. Why? Because the standards are different. You think this one means good. I think that one is good. So that's a very, very terrible problem, that you don't know how to measure the goodness or the success here, which is described in this part. In this lecture, mostly I define the similarity or dissimilarity. And in many cases, I directly start from L2 norm, which means the Euclidean distance, to make my life easier. In different problems, you may want to use different, measure. Okay, so one thing is that because in terms, of the joint probability distribution, here I only have x without a y. In other words, I have to directly estimate this px. It's very different from the supervised learning that we never consider this. Usually what we do is this or this. Here, you have no choice but directly estimate this. If p is a small number, very good. We can use some statistical methods to, did I give you a midterm exam, Arab? Which is the kernel method here? No, I didn't give it to you. I forgot. Which is usually use the density, use the surrounding area divided by the total area to estimate the density, the marginal density actually. But that method doesn't work if p is a large number. Why? Curse of dimensionality. Remember the KNN case, the square, the cubic that I drew on the whiteboard? No, I remember that case. Arapa was the only student there. Yes, you're the only one here. Remember, I drew a kind of like very, very small cubics on the whiteboard at the time, and also I ran it in the Excel about this part. But curse of dimensionality is a killer of many, many standard traditional statistical methods. And because of this, we cannot directly estimate it anymore. Instead, what we're going to do is that we're going to use descriptive statistical methods to directly describe it, the characteristics of px. And in the course here, I'm going to introduce two parts of these descriptive statistical methods. The first one is clustering, and the second one is principal component analysis. Both of them are extremely important. I personally would say the most important in unsupervised learning, excluding this kind of neural networks or something, this kind of deep learning things. I'm talking about standard machine learning things. I personally believe these two are the most, among basic methods, these two are the most important two methods. If you want to know more about this, read chapter 14 about the ESL, the textbook. Okay. So in the following, let's introduce the concept of clustering. So the basic idea of clustering is in this way. Suppose I give you some data. Be careful. The original data, you don't have the three colors. Just imagine all of these colors are black color. They're all together just. So the clustering is that I want to group the data into subsets, for example, into K clusters in a way that objects in the same cluster are more similar or more closely related to each other than to objects in other clusters. So for example, in this case, it's actually already given by the color. You can see it's kind of like here is kind of like one cluster, one group, kind of like here is one group and here's one group. See it? So this is the point of clustering. You may say that, okay, so suppose you've already had these three groups. For example, oops, so ugly. For example, you have this, and this. So what, right? Okay. So what? The point is that have a look at here. Originally, what is your feature space? Your feature space is the whole R2 space. Okay, now suppose I have the cluster, the 3 clusters here, and suppose, the clusters here are, are done very successfully. Suppose, okay, so that you no longer need the whole R2 space. You only need these 3 groups, especially the information of the centroid. See it? And that's the point of clustering, that instead of given or using the whole feature space, I can cut it into multiple, this kind of subspaces, which are simpler and smaller. Then when I'm going to describe or I'm going to characterize the data, it's going to be easier for me. That's the point of clustering. Okay, so first of all, for the clustering, we mentioned here more similar or more closely related. Then the question, what does similar really mean? Similar, how to measure the similar here, right? So to this point, what we use is a measure. Mostly this measure would be an L2 measure, but later you're gonna see you can use L1, correlation or L0 measure. To formally address it, let's consider this part. Let me see. Can I use this part? Let me use this. Okay, so okay, let me use this. So first of all, what I'm going to do is that I'm going to define this similarity or similarity the same. So we're going to define this similarity by this notation. The il and xjl for the dissimilarity of feature L between data I and the data J. Then the dissimilarity between two data, xi and xj, is defined by this way. The summation of all features of L, of the DIL and the XL. So in this case, we defined the dissimilarity between two data. Be careful here, okay? IL and the JL means what? The I's data, the L's feature, and the J's data, the L's feature. And then summation of all the L's becomes the dissimilarity of the two data, okay? And of course, in some cases, you may say, hey, what if I have a preference in some specific feature? Okay, in this case, you can add a weight WL here. It doesn't matter. The reason I add a parenthesis here is that if I don't add a parenthesis here, I don't know why, LaTeX make this L and the D very, very close. Looks like a WLD. That's the reason why I add a parenthesis here. No other meaning, no worry. Okay, so in most cases, this D, about two data in feature L is defined by the L2 measure, which is the Euclidean distance. The same as what we did in the supervised learning, see it? But again, be careful here. This measure is subjective, not objective. You know what I mean? Because in many cases, many applications, the difficulty is how to define the measure itself. That's why it is kind of like subjective rather than objective. Again, because you don't have a teacher, you don't have a common standard that can convince everybody. Okay, so this is the problem. Okay, now if we define in this way so that I have the measure of the dissimilarity between two data. The question is, if I don't like the L2 norm, do I have any other options? The truth is yes, you definitely have something else. As what we mentioned, introduced in the beginning of this class, for the loss function, remember, you have L1 loss, which is absolute loss. You also have 0,1 loss, remember? The same here. You have L1 measure, which is the D between xi and xj is the L1 norm, or you have the 0,1 norm, or you have correlation norm. Why correlation norm? Because in unsupervised learning, many cases you want to kind of see how uncorrelated or how correlated the two data are, so that you may use the correlation measure. The interesting thing is that, so this is the definition of the correlation measure. The interesting thing is that when you're doing the correlation measure, it can be showed that this part gonna be proportion of 2 minus the correlation of xi and xj. And hence what? Hence the clustering based on correlation similarity measure is equivalent to the clustering based on L2, this similarity measure, because there's a negative, okay? So here is a similarity, this is dissimilarity, or vice versa. If you call this one as dissimilarity, so this is similarity measure, okay? And another thing, be careful that X bar I here is what? X bar I here is the mean of feature is the mean of Xi about all features. It's the mean of the features, not the mean on the data for a specific feature. This is the mean of a specific data of all features. And this 4 is nothing but the definition of correlation. Okay, so actually, basically, you still have what? You still have L2, L1, L0. Correlation is actually the same, similar to L2 norm. However, in many cases, you're going to see correlation measure, which is, too many in many this kind of problem. So after defining the dissimilarity, and also we know the definition or the motivation of clustering, we can immediately follow it to integer programs. And for this part side, I guess you're gonna love it. Why? Because this part is some methodology that we used in the research. That three indices and 2 indices models. The problem, the thing is that the 2 indices or 3 indices models here are much easier than our research. So I guess you can immediately find it. The formulation here I wrote is much easier than the formulation you made in that part. Okay, so first let's have a look at about the integer programs here. So remember, the purpose of clustering is what? The purpose of clustering is to group data into subsets in a way that objects in the same clusters are more similar to each other than to objects in other clusters. Okay, now we've already had the dissimilarity measure, which is dxi xj. Suppose this is known. In other words, for a given xi xj, suppose this is a constant. Okay, what I'm going to do is that it's kind of like an assignment problem. I'm going to define a binary decision variable zik equal to 1 if data I is set to be in cluster K. And I'm going to set delta ijk equal to 1 if both data I and j are in cluster K. So in this case, you can immediately write what? You can immediately write an integer program by this 5. So the constraint, so the objective function here is what? As the summation of the total dissimilarity, okay? We want to what? We want to do this. We want to minimize the summation of within cluster dissimilarity for all clusters, right? So I'm going to count for cluster K equal to 1 to K. This K is big K, okay? And then for each data I and j, here I set j is greater than or equal to I because otherwise I will have a half here, because ij and j will be double counted, okay? I assume this d is symmetric, so that dxi xj equals to dxj xi, they're symmetric. So I don't want to have a half here, so that I set j equal to I plus 1. You can definitely write here as j is not equal to I, and then put in a half here, okay? So for each data I and each data j, I'm gonna do what? I'm gonna measure their dissimilarity and times delta ijk. That I'm gonna count this dissimilarity if and only if both I and j are in cluster K. Said, feel familiar? Hello? Said, are you there? You're muted. Anyway, feel familiar about it? The what? Our VRP formulation is the same. Remember it? Hello?
Problems. Okay.
Okay.
Yeah. It's similar to 3 indices VRP formulation.
But it's much easier because in VRP formulation you need to use a lot of MTZ or symmetric, strengthen MTZ things to construct a symmetric, thing to eliminate the subtool. Here you don't need to worry about the subtool. So you're gonna see the formulation later. It's much easier. Anyway, okay. So actually, remember at that time you asked me, where did you get the idea to get 3 indices or 2 indices, right? It's from here. Because I saw somebody, this file is written by someone else. And I feel not comfortable. So I built this one by myself. anyway, just for fun, not seriously. Okay, so the objective function is to count to count the dissimilarity for each clusters. Okay, so constraint phi b is for what? Constraint phi b is let me see what's the meaning of constraint phi b. Phi b here is that for each data, it must be assigned to one cluster. And constraint phi c means that no clusters can be empty. Because I said, for example, I need to have k clusters. K clusters means each cluster should have at least one data. Otherwise, it's not a k clusters. So this tells you that no cluster will be empty. Constraint phi d is the definition of delta ij. So this means that if and only if both zik and zijk equal to 1, then your delta ijk will be 1. Otherwise, delta ijk must be 0. Okay, so after this, then it's going to be exactly the same meaning of our the definition of our clustering, given the dissimilarity measure that group data into subsets in the way that objects in the same cluster, which means the within cluster dissimilarity will be more similar to each other than in other clusters. Here is to minimize the within dissimilarity for all clusters. So this is the integer program, very simple one. However, the bad point is that I have a delta ijk, and in most cases you dislike this delta ijk. Why? Because ij will be large, so it's O(n) squared times k, big K. It's very large. The truth is that here in this model, I only have delta ij. See it? I saved one index. So saving one index means you can save k times. That's a lot. It's really a lot. The truth is that who cares whether ij belongs to the same, who cares where ij belongs to? As long as they are in the same cluster, I'm gonna count, right? Okay, now how to define this way? So here I define delta ij to be 1 if data I and the data j are in the same cluster. And the same definition of zik equals to 1 if data I is assigned to cluster k. The point is that here again I don't care as long as ij are the same in the same cluster, regardless of which cluster, I'm gonna count it. Then this very easy. 6a is the objective function, and 6b the same. 6c, 6b means each data will be assigned to only one cluster. 6c means what? No cluster will be empty. And have a look at 6d. 6d shows you what? Think about this. Zik and zijk, how many possibilities you have for a specific k? You have only 4 cases, right? Both 0, both 1, 1, 0, or 0, 1. Okay, if I write a constraint like 6d, what does it mean? That means that if both of them are 1, then delta ij must be 1. See it? That tells you what? That tells you, okay, if there exists a cluster K such that both I and j are in cluster K, then delta ij must be 0, must be 1. And you may ask, so how about the other cases? 3 cases. Let's say both delta ik and delta jk equal to 0. Okay, so you're going to have delta ij is greater than or equal to 0. Greater than or equal to -1. That means it can be either 0 or 1, right? Looks like there's a problem. I mean, you didn't really give me an selection. Actually, it does have a selection. From where? From this objective function. Suppose you don't specify delta ij. Let me ask you what the value of delta ij will be. It's going to be 0. Why? Because we are to minimize this function. See it? And the dxi xj is always positive. At least it's non-negative, unless trivial cases, it's going to be 0. Otherwise, it's always positive, right? So that if I have a choice to make delta ij to be 0, the solver or the problem will what? Will set the delta ij to be 0. See it? In other words, this shows you what? This shows you that if zik and zijk are both 1, then your delta ij will be 1. Otherwise, delta ij will be 0. And in this case, very clear, right? This 6 will be equivalent to 5. So what is the point of making 6 if we've already had 5? Because the formulation of 6 here includes nk plus n choose 1. decision variables. By comparison, your formulation 5 has nk plus n choose 2 times k. Why? Because, for example, have a look here. Nk is from where? Nk is from z. Your I has n choices, k has k choices, so here I have nk. How about the delta ij? Delta ij is n choose 2. That's why the number of decision variables in formulation 6 is nk plus n choose 2. How about in formulation 5? It's different. Why? Because you have delta ijk. N choose 2 times k. See it? And hence, how many decision variables can you save? You can save a lot. The difference is a factor k here. That's the reason I want to have 6D. I want to have 6 formulation rather than 5, okay? So any questions here? This integer model is super simple. You guys should be able to write it by yourself.
I have a question.
Yes.
So it's not a question. In fact, we can say that it's not the case that always number of clusters are given, you know, because sometimes we don't know how many clusters do we have, and then we want to determine it based on the data set that we have.
That's a very, very good question. Actually, that's a big problem of most cluster methods. That is how to determine the k. There are many different methods. The easiest method, of course, is kind of like a balance, because think about this, especially in image processing. Later, I think I have some examples of image processing. In summer, I'm gonna put my cats there. This time I don't have enough time to make my cats there, so I directly copy and paste this picture from pattern recognition. This is the author's son, very cute, right? That was 14 years ago. Now probably already a big boy. Anyway, so in this case, what people did is that people just increased the k, and then they have a look, you know what I mean, at the picture, until the case that, for example, the picture is not too bad. Then they're gonna apply the picture. That's usually what they do for the image processing. And there are other statistical methods. One of the methods is something like this way. For example, you're gonna draw the case, and with respect to the error, the summation of the dissimilarity. So with the increase of k, you should see it's gonna be decreasing the number of errors. What we're gonna do is that we're gonna see, for example, something like this way. Suppose something like this. No, it should be this way. We're gonna see something like this. So here, all of them are more and more until this point. This point here, you can clearly see it's the decreasing. No, actually, this point is already like this way. Decreasing, you know, consider the rate. The slope here is decreasing, see it? And after it's going to be slower and slower. In this case, we're going to take this point. We choose this k. However, there's no general methods for determining the k. It's very, very subjective. I mean, different people may have different way. The most common method, again, is by visual inspection, especially for this kind of image processing. We're going to try different case until a k that I feel is not too bad. Then I keep this k. That's it. And in many cases, you can see, have a small k, the result is pretty good, actually. I don't know whether we have time to finish it, or probably it's going to be in the next class. I will show you an example using my cats. I have the pictures here. Use this picture. I'm going to show you because I played it in the MATLAB just now, and I realized that a small k actually gives you very, very good results. I have two pictures. One picture is this baby is angry. The second picture is this one is yawning. So it is something like this. And then I'm gonna do the k-mean clustering by MATLAB, do image segmentation, and you're gonna see some very interesting results. But again, this time, because I'm kind of like too hurry writing this part, I didn't put the picture there. I guarantee you in summer, I'm gonna update, use my cats instead of, you know, to make my class notes unique. Okay. Any other questions? But Said, this is really a very good question. It's one of the most important research topics today, how to determine this k in clustering in general. Any other questions? No? Okay, and then let's continue. The main topic here regarding the clustering is actually the so-called k-means clustering. So first of all, in the k-means clustering, we assume this k is given, okay? So this k is a constant. What we're going to do is that the motivation of the k-means clustering is that, first of all, k-means clustering is probably the most popular clustering methods. When we say clustering, usually the first thing that you're gonna hear is k-means clustering. Why? First of all, let's see what is the motivation of k-means clustering. The motivation is that we want to assign the n data objects to k clusters such that the sum of these, here we use the Euclidean distance, L2 distance of the object to its cluster centroid. Here, k-means means k-centroid, okay, is minimized. Okay, so this is the original motivation or definition of k-means clustering. Interesting thing would be what? Interesting thing is that later you're gonna see this k-means clustering is a very natural derivation of this general model. And you're gonna see, in addition to a small revision, they're equivalent. It's really amazing. And by the way, Mahbooba, remember last year, one of your research topic was what? Was something with Dr. Pan about the clustering problem. Remember it? And you know what? By some chance, I realized that to use this method, we may find his results uniquely, independently by this formulation rather than by his methods of that, that way. And I guess at least 80% we can do it. Let's try to play it. If you have some time, we can use another method to formulate this one to be the 0-1 SPD. And actually, personally, I'm very interested to solve this problem. No matter 5 or 6, they are nothing, the same. To solve this problem. Solve means find an efficient algorithm. Because if these two problems are somewhat similar and he can formulate that problem to 0-1 SDP, this one must be able to follow to at least as simple as 0-1 SDP. And we should be able to get at least 2 approximation method for solving this problem. But it takes time. Later we can discuss, in summer for the details. And this is gonna be an independent way, not using the method that he used here. Anyway, he used it there. Anyway, okay, so, but at the current stage, let's forget about this. Forget about the equivalence. Later, I'm gonna prove why it's equivalent. Let's just directly, purely from its original motivation. That is, I wanna find the k-means clusters such that the n data to these k clusters will minimize the sum of the distance of the data to its cluster centroid. Okay, let's see. So mathematically, we're going to create the model in this way. Excuse me. First of all, let Ci denote the cluster which data Xi belongs to. And then let's denote mu k as a centroid of cluster K. Okay, and then that's very clear. Suppose I have already the mu k. Suppose I already have the Ci and the Xi's. How would you define mu k? Very simple. I'm gonna summation all the Xi's that belong to cluster K and then divided by the number. Nk means how many data are in cluster K, right? The summation of all of them divided by number, that means what? It is the centroid, right? You've all learned physics. For example, I have a rubber here. You cannot see. Let me see. Where's my video part? Let me turn on my video part. So for example, I have a rubber here. Let's say a water, whatever you want here. How to get their gravity point? Simple, right? Suppose, oh no, this one's difficult. Why? Because it's it's not evenly distributed about the what about the mass. Let's think about a rubber. Rubber is equivalently distributed. So what you're gonna do is that you're gonna build this rubber in the 3D, and then you're gonna do what? You're gonna sum over the x and the y and the z, divide by 3. Remember it? And then this sum is integral, actually the integral. And then in this case, you're gonna find what? Find the gravity point, right? That's the very basic physics that you've all learned in high school or in, let's say, elementary. No, elementary, you have not learned calculus, or in your first year of undergrad, right? So similar here, suppose I have let's say, nk points in this cluster. How to find the centroid? composed by these nk points. Simple. You sum all of them and divide by nk. Done. Okay. Now, after having the centroid of this one, the k-means clustering is to do what? To minimize this one, isn't it? Again, by the definition of k-means clustering is what? The definition is to minimize the n-class, or to minimize the distance of the data to its centroid, cluster centroid, for all clusters. That's why you need to first sum the clusters from 1 to k. And then this means what? This means the data I, the distance from the data I to its what? To its centroid, square, to norm. And this is the meaning of k-means cluster. Okay, and be careful that this part is actually what? This part is actually a representation of what? A representation of variance in cluster K. See it? Why? Because variance is what? Variance is nothing but this part divided by nk, right? Because mu k is the mean, okay? That's why it's called k mean or k centroid. Mu k is the mean. Data minus the mean divided by the number of data, isn't it the definition of variance? Okay, so that I can equivalently write this definition to be this. From k equals to 1 to capital K of nk times the variance of sk, where sk is the set of the data in cluster K. Okay, so this is actually to minimize the variance times nk. Okay, now we have already mathematically defined it, but it's still not comfortable enough. Why? Because here I directly use this notation, I, such that Ci is in K. But what do you mean? Because in this case, I'm actually what? Trying to find the partition, or trying to find this assignment Ci. See it? Do we have an integer programming formulation here? Yes, you did have. And this is a very simple and a direct way. Habuba, can you independently find it? That's the homework last year I asked you to do.
Yes, I did.
Okay, good. This is really, really simple, okay? This one, also you can find it from the paper, which is Dr. Pen's paper here in 3. This is a very, very good paper. I would highly recommend every one of you to read this paper. Very good paper. So that, you know, I define Zik to be with assignment variable, the binary variable. If Zik equal to 1, that means data I is assigned to cluster K. Okay. And this part is what? This part, let me use this part. This part is actually the mu k. See it? Why? Because zjk here means whether data j is in k. So the summation of zjk times xk means what? Means for all the data that is in cluster k. And this part, the denominator means what? The denominator means nk actually. How many data totally are in cluster K? See it? And hence this part, this part is actually what? The centroid of cluster K, which is mu K. Okay? And this here, here. And this Zik here means, well, whether this data I is in cluster K. If it is in cluster K, I'm going to count. If it's not in cluster K, I'm not going to count it. Okay, so that is the meaning of for each data versus the cluster. If it is indeed in cluster K, I count it. If it's not, I'm not going to count it. And for these constraints are exactly the same. You know, here each data must be assigned to one cluster. Here each cluster must be what? Must be non-empty. Okay, so this is the integer program formulation. But be careful, this is nonlinear, not linear. Okay. Nonlinear. And in Dr. Pen's paper in 3, it has showed that this can be reformulated to be a 0-1 semi-definite program. And later, let's use the methods that I played here to independently make it. Probably we should find the same answer. I would be very glad if we find another different answer. That means great. We can publish a good paper probably. Okay, so after this, are we done? No. We still need to solve 2 things. First of all, for example, if we have already had this problem, so why don't we directly solve this problem? Why should we, for example, later to use some heuristic methods? The reason is that this problem is NP hard. And for this problem to solve explicit, the exact solution for a huge N, it's gonna cost your whole life. So don't try it. It's meaningless. By the way, actually in this part, in this section later, I'm gonna prove that this formulation is kind of equivalent to this formulation for L2 norm. And that's the reason why this problem is also what? This problem is also NP hard, okay? And here's a question for Said. Said, are you here? When you see this problem, can you immediately find the method of branch and cut? Branch and bound, actually. Have a look at this problem. It looks like what? Looks like one thing, which is also the method you used in your research. Actually, even simpler in your research. Assignment problem. See it? Except for phi d, this is actually an assignment problem. See it? Okay. Now for assignment problem, we have what? We have Hungary's method. How to read this word? Hungarian's method, right? Which is a polynomial method. Okay. Then what you do? Danzig-Wolff decomposition. See it? And immediately you can use Danzig-Wolff decomposition, and inside use what? Use the assignment problem, and then you can do the branching. Get it? So of course, this is a very traditional way, and it's approved. Okay, unfortunately, it's approved that this method is not that effective. That's why I want to use the technique which was built here to formulate it to be a 0-1 semi-definite program, and then to redo it. Probably it's going to be faster. But the reason I ask you to look at it because this is exactly the same idea that we tried it before, remember, to solve your problem, Danzig-Wolff decomposition. And also we tried the assignment problem, and then use the patching method, patching algorithm to revise it. Remember it? I cannot hear you, sorry, because you're muted.
Yeah, okay. So if we want to use Danzig-Wolff decomposition for this problem, so the Danzig-Wolff decomposition is used to
for the variables.
No, it's used to formulate to solve the problem using branch and price. You know, because when we have Danzig-Wolff decomposition, what does it mean? It means that we have a numerous number of columns, and then we don't consider all those columns at the same time. So it's a column generation and row reduction, which is nothing but branch and cut. For dynamic for integer programming, it's gonna be branch and cut. But for continuous programming, no, it's column generation, just column generation.
No. This is not continuous.
Yeah, I know.
It's integer, not continuous. Continuous, it's done already.
Yeah, exactly. So since it's integer, we need to solve it using branch and cut.
Yes.
Yeah.
Because what you are doing is the branch and price, right? Because you're gonna find the maximum reduce the price and then add this column inside. The key reason, because to look at a phi b and a phi c, they are what? They're assignment constraints. So that you can ignore this phi d. You solve this first and then add it. That's the point here. And this is something you can do here. And unfortunately, it was already done. And fortunately, it's very slow. It was slow, so it's good. That means some people can do more work. If it's really fast, then nothing you can do.
So you mean the Danzig-Wolff decomposition has been done and it's a slow?
Yeah, this part using this structure, because this is phi b and phi c looks like what? Assignment problem. So first we solve this problem first. Be careful. What is delta ijk? Delta ijk is nothing but delta zik times zjk. Okay, and then you can decompose it, and then we're gonna solve phi b phi c first, and then ignore this phi d, and then gradually consider the phi d and add the columns. That's it. So that's the reason why this is a very, very immediate observation. You're gonna get it. Why? Because the structure is really too beautiful. Directly, assignment type of structure. It's too simple. The problem is because everybody can see it, so everybody gonna use it. And the structure using this way, it was already proposed and solved like in 1980s or 1990s I think, or 1980s I forgot. And it was the good point is it's really not fast. It's proved to be very slow. I don't know how about this 0-1 semi-definite programming. If it's faster than that one, that's going to be good. I haven't checked very carefully about the literature. I don't know anybody did it. Excuse me. I don't know anybody did it directly, you know, from this from this formulation or this formulation. However, 100% sure that somebody already did it for this formulation. That's why I said we can independently kind of formulate that problem to be a 0-1 using this way, this proof way, rather than if you have a look at Dr. Penn's proof way, you're gonna see uses a lot of matrix, which is to solve this part. You know how to take this one out, use a lot of skills. But actually, if we can use this conclusion, then they should be equivalent. Anyway, let me first finish this part. So it's important to see the relationship between this 10 formulation and this formulation, this 5 or 6 formulation. And in the following, I'm going to prove that they're equivalent, in addition to a very small modification to add a coefficient there. Due to time limit, let me make it very fast. So from 10, first of all, as we mentioned, this part is nothing but actually the mu k. So here, to make my life easier, I'm gonna directly denote it to be mu k instead of write so many big, so many formulations here. Okay, now let's see how to decompose it. So from here, we have sigma of I, Ci is in k. So this represents the Zik actually. This one equals to what? This one equal to, you take the norms out, it's going to be xi norm plus nk times mu k norm minus this, okay? And this one is very simple because this part equal to what? This part equals to 2n mu k square, see it? Because mu k equal to what? Mu k equal to the summation of them divided by nk, right? So 2n and n cancel. I have this part, minus n. And this part, again, mu k equal to what? Mu k equal to the summation of xi, I in k, ci in k, and divided by nk. So this part, again, equal to this part. And then you just, do some very simple math, and you're going to have this part. So here is the value of this, which is directly from the objective function of 10a, okay? Now let's have a look at the 4a or 5a. Let's have a look at, for example, 5a, this one. What does this look like? Now our D measure, the dissimilarity measure has been what? The 2 norm, L2 norm. So that actually I'm calculating this one. This one, again, let me ignore this I is greater than J, right? It to be I is not equal to J. This is half of this. And then similar, I just expand it and then do some math. And then finally, I'm gonna have this and hence this. And if you compare this 12F with this 11D, you see what? You see 12F is nothing but NK times of 11D. See it? And hence, they're equivalent actually. So that the k-means clustering problem is actually a natural derivation of the general clustering problem in 4. The difference is here. You need to add a NK. And NK can be expressed by what? Can be expressed by the sigma of ZLK, right? That means, okay, how many numbers, how many data are totally in cluster K, so that you can express 10A to be in this form. The part of this form is actually what? In the form of what? Of 5A. That's why if you ignore this coefficient NK, they're equivalent. See it? And that's the reason why just now I said we may directly formulate this problem, the problem 5 or 6, to be a 0-1 SDP directly using this idea. Expand the matrix form in this way instead of using that way. In my personal view, this way is much easier than that way. That way uses kind of, you need some tricks about linear algebra things, but this one is super simple. You just expand everything, you can get it. I'm not pretty sure it's possible that we're gonna have exactly the same result, or maybe something newer, which I would really be happy, something, and we need to explore it a little bit. Okay, so let me see. Okay, due to time limit, I'm gonna leave the k-means algorithm in the next class. And in the next class, because this problem is NP hard, it's almost impossible to solve it, in real applications when n is big. So we're gonna use this k-means algorithm to solve it. And then later, you're gonna see the case that for the clustering, it's really good. And for the image segmentation, you're gonna have something like this way. And all of them are done by k-means clustering. And I'm gonna show you the example of my cat, and you're gonna see how it really works. And it really works very, very well. And also as a very good, very, very simple and a powerful tool for image compression or data compression, that you no longer need to store a huge image. You just need to store a relatively small points, which are the centroids of these clusters. And then if you can, have some further powerful tools, for example, kind of like consider, let's say, for example, n1 by n1 pixels as a 1 unit, you can even, compress it bigger. And then as long as you record the rule, then you can recover this image. That's a technique of image compression and recovery. Very, very powerful things that we can currently using. Okay, so I'm gonna leave all these kind of detailed examples in the next class. And again, as we mentioned before, next Monday, we will have an extra class. That's everything. Thank you very much for today's class.
Yeah, I have
Okay,
one
good
question
evening. Yes, thank you. Bye.
about.
Me too.
Hello.
Yes, yeah, question?
Yeah, about homework actually.
Yes.
So that if I just write the code for Cholesky decomposition and keyword decomposition, is it enough if I write my own code?
Yeah, you can write your own code, or you can calculate by your hand. It doesn't matter.
No.
I would suggest you to write your own code, but it's not required.
Okay, so if I write my own code, do I need to show step by step everything, or just need to submit the code?
That's a good question. That's a good question. Well, I think no. You just give me your MATLAB code.
Okay.
Yeah, and then I'm gonna run your code to see whether your codes are correct or not. But of course, you need to show me the result. Of course, in your use the Word, right? Your Word document clearly show me the result.
Okay.
Yeah, everything here you can code by yourself, including this k-mean clustering. Very interesting. If you don't believe, just after next class, you just take one of your photo by yourself, and then compress a photo from. Usually, for example, you use your iPhone to take the photo, and it's gonna be big, right? For example, it's 1,000 by 1,000. That's too big. No, instead of 1,000 by 1,000, make it to be 200 by 200. In other words, make 5 pixels to be 1 unit. Trust me, our eyes cannot really differentiate these 5 pixels. Humans' eyes are not that accurate. And after that, use this k-means clustering and send it to your wife or to your girlfriend and ask her whether you can recognize me. If you cannot come to talk to me, that means the method that I taught to you is wrong. Because even your girlfriend or your wife cannot recognize it, then there's some problem. Probably they can recognize. And the more interesting thing is you can sing a song and record the song to MATLAB. Do you know how to tune it? And then use the matrix, read the matrix of the song. But be careful, in MATLAB, if you record the voice, there are 3, kind of like RGB, there are 3 main components to record the noise, to record the music or the sound. I forgot the details. When I was a PhD student, I played a little bit. My singing skills are pretty bad. And then me and my roommate, we try to modify our song to make it as good as a professional singer. Of course, finally we failed. But you can use the k-means k-means clustering technique to kind of compress your data, so that your song may not like a human song, may sound like something very weird, but at least you can record it, so that to make it to be a smaller size, so at least the people may hear the sound noise. It doesn't matter whether they can recognize it's a human song or not. But anyway, it's just a joke. But to be honest, in some cases, if you are professional in doing this kind of signal processing, and the truth is, yes, you can really store it in a way that people can recognize it. And meanwhile, it's going to greatly reduce the size of the file. Anyway, regarding the picture, we're gonna see it in the next class. Okay, that's everything about today's class. See you on Wednesday. Bye bye.